Okay, so in the second video, I'll touch on another type of quantization, which is non-uniform quantization. Okay, so for non-uniform quantization, we'll just briefly go through the concept, and there won't be any calculation except for this SNRQ. It's just because it's much more complex than the uniform quantization. Okay, so non-uniform quantization, it was introduced to further improve the uniform quantization. So for non-uniform quantization, the levels, the intervals between levels are not fixed, are not the same. Okay, if you notice, uniform, they are all the same from the lowest up to the highest level. The delta V always similar, fixed. But non-uniform, the delta V changes with our intervals. Especially since it want to improve the quantization SNR for the lower level amplitude, we'll have more levels. More levels mean the delta V will be smaller for low level amplitudes compared to higher amplitude. So by doing this, we can further increase the SNR of the lower level amplitude and but decrease SNR for the higher amplitude. So there's a it's a trade-off. Yeah? So in this non-uniform quantization, we have a concept as known as compending. So compending actually refers to two processes, which is the compression and the expanding or expansion. Okay, so basically to produce uniform SNRQ for all input range. So there are two types, analog and digital compressions. Okay, so analog, we do it before we perform our analog to digital ADC. For digital, it's after our ADC. And analog compression is at the transmitter, while expansion is at the receiver. And this is the formula for non-uniform quantization. Okay, so this is the SNRQ for if you use compending that uses mu law. There are certain rules for this non-uniform quantization. One of them is mu law, and this is the SNRQ for mu law. So this, the whole part is here, and when you solve, it's in dB. Okay. So when you solve, you need to be careful a bit because this holds in dB. This is one part. When you solve this, 10 log of term inside here, it's already in dB. Okay, and then so this one is also already in dB, and it's our number of bits. Okay. Oops. Okay, so there's here we compare between uniform and non-uniform quantization. Okay, so we have two signals, the strong signal and weak signals. Strong signal are the signals with high amplitudes, and weak signals with, you can see here, low amplitudes. So like this one, the voltage ranges between quantized level 6, 7, 8, around that. Okay. So if we use uniform quantization, okay, like over here, okay, this point is quantized to level 8, and this point to 7, and also the rest rounded to 7. So there are only two levels to represent the signals. Okay, so when we during the detection, if you want to recover the signal, it will just show like square wave, something like that. It's not smooth. Okay, so this one has high error compared to the strong signal. So the strong signals, it's not too bad. You can still see the sine shape. So for if you use non-uniform quantization, okay, for both weak and strong signals, you can notice here, okay, at this region where we have smaller amplitudes, yeah, the intervals is less compared to the high level amplitudes. You can see the gap, the delta V here is bigger, and then it's become less, and here also very small, and then when it goes to higher amplitudes again, the step size or the quantization interval will increase. Okay, so this is known the quantization interval is also known as step size. Okay, so you can see more levels used to represent this weak signal. So when we during recovering process, much better compared to this weak signal. Okay, so compending, like I say, is the combination of compress and expand. So at the transmitter, signal is compressed. Like here is one function, yeah, that is used to compress signals. So you can see in this function, the signals in the middle with low level amplitudes has linear. The signals here has linear relationship compared to higher level amplitudes over here, top and bottom, it's compressed, meaning that if you can see the range here, this is our input, this is our output, how they are compressed. Okay, and at the receiver we'll expand using the same function. So, and you can see here the input is narrow, output is wider. For the middle, it's not changed, linear. So this is a function, one function to perform compending. Okay, so for analog, compression is done before ADC and expansion after DAC. For digital, okay, so we have to do it after ADC, because of course digital compressor deals with digital signals. We need to finish the ADC process first, and then expansion before the DAC. There are two laws that are popular for this compending. In the law based in Europe is known as A law. US and North America use mu law. Okay, so this is the function for A law. So this is our input and our output. So in here you cannot see X is the normalized input, Y is the normalized output. So okay, normalized meaning that we have to divide X and Y with the maximum and minimum input and output voltage. Okay, so over here, different A will give us different relationship. If it's A equal to 1, it's just linear, no difference. But higher A, okay, you can see higher A, if our input is 0.2, our output is nearly 0.8. Okay, normally value of A is 87.6. And for mu law, almost the same concept is used. Okay, typical value is 255. So this is the equation for Y given mu. Okay, so if our mu is 0, then no difference, higher 255. And we can see the compression is more effective over here. So to get the value x and y, we have to divide with input voltage maximum and output voltage maximum. Okay, that's what we call as normalized. Okay, so let's try this example. So a compending and compressed expense system using mu law, mu 255. So input signal is between 0 to 10 volt. Find the output if the input is 0 and 7.5. Okay, so first, this is the equation that we'll use for our this mu law. Okay, we need to find what is our x. So for the first part, when our V is equal to 0, x is equal to 0 divided by E1. So our maximum voltage is 10, so it's 0. So y is then equal to log 1 plus 0 divided by log 1 plus 255. So log 1 divided by log 256. Okay. So it's 0 lah. Because log 1 is 0. So y is 0. For the second part, where v is equal to 7.5, x is equal to 7.5 divided by 10 is 0.75. So we put inside our equation log 1 plus 7, not 7.75 times 255 divided by log 256. Okay. So if you solve this, we got log 255 times 0.05 plus 1 log. So this one we got around 2.284 divided by log 256, 2.41. So 2.284 divided by 2.41. So around 0.95. Okay. All right. So this is an example for compending using mu law. So like I said, for non-uniform quantization, we don't design or solve the quantization scheme itself, because you can see because of the changing step size, it's more complex, which is out of our scope. Okay. Next is we're given random signal with 256 uniform quantization process. Determine the quantization signal to noise ratio for this system. Okay, so our L is equal to 256 and it's uniform quantization. Find the SNRQ for uniform is 1.76 plus 6.02 N dB. Okay, so L256 using L equal to 2 to the power of N, then our N is equal to 8. So 1.76 plus 6.02 times 8 is equal to around 49.92 dB. Okay, so equation for non-uniform SNRQ will be given. I think also with uniform, but this one is much shorter and easier to be memorized. So there shouldn't be much problem. Okay. All right, so I'll stop at this part. Okay, and then I'll continue with another video on delta modulation.